If you want your 3D printer to be fast, you need a motion system which can move as quickly as possible and an extrusion system that can push and melt plastic fast enough to keep up. Whichever is slower will determine the maximum speed you can print. Flsun seemed to understand this when they designed the V400, since it has a high flow hot end and delta kinematic system boasting an advertised print speed of 400 mm per second. But unfortunately, marketing numbers and reality often don't quite see eye to eye. Have Flsun overestimated their printer, or could it possibly be that they've left performance on the table? Today, I'm going to test the maximum capabilities of the V400 to find out how fast it can really go. Today's video is sponsored by Flsun, so I'll be sure to keep all my evaluation free from my opinions and just focus on objective measurements from the testing. Unlike the classical motion systems used on 3D printers, where a single motor drives a single direction, the V400 uses a delta kinematic system where 3 independent motors move carriages vertically, which in turn attach to linkages and the effector or tool head. The result of this is a low moving mass, which should mean high acceleration. On the extrusion side of things, the hot end is similar to an E3D volcano. It has an elongated melt zone, providing greater surface area for melting filament, compared to a standard design. The extruder is based on a Bondtech BMG using their dual drive system and a similar gear ratio, but instead using a round NEMA 14 motor. First, I'll test the Delta style motion system for maximum speed and acceleration, and then the extrusion system for maximum flow rate. From that, we'll identify the optimum performance of the V400. When testing for maximum performance, it's important to understand that stepper motor force varies with speed. Therefore, we have to balance speed and acceleration. So our testing will find how they relate to one another. So to test the motion system, I'm going to use the large small pattern method. This test is based on an open source Clipper macro by Andrew Ellis, where the toolhead moves through a large cross box pattern and then a small cross box pattern. That original macro has been enhanced for my testing today to test a full range of speed and acceleration values with a single command. I'm going to test speeds from 300 to 1200 mm per second. For each speed, I'll first test a large range of accelerations in steps of 10,000 mm per second squared, testing 2 iterations at each step. Once that test fails, I then repeat the search in a smaller area near to the failure with 1000 mm per second square steps at 10 iterations each. The final value is the last successful test before failure, which then should be accurate to 1000 mm per second squared. At higher speeds, I'll also increase the small pattern size a little to allow the toolhead to reach maximum speed. These are the results. This curve here is the acceleration speed curve for the V400. Anywhere below the curve is within the capabilities of the mechanical system. Anywhere above will result in skipping, missed steps, and other general printing disasters. This point here is the recommended settings from the factory, around 400 mm per second maximum speed and between 4 and 7000 mm per second squared acceleration. From my testing, at those same speeds, the V400 was able to achieve 132,000 mm per second squared of acceleration. I also want to point out specifically that at 300 mm per second, even at 500,000 mm per second squared of acceleration, there was no indication of failure. As we increase speed, however, you can see how the acceleration drops rapidly, but once we reach around 800 mm per second, the peak acceleration starts to level out. We'll look back at this diagram a little later though. For now, we need to test flow rate. If you're interested in testing like this, don't forget to subscribe and check out vector3d.co.uk for 3D printer upgrades, tools, and accessories. The most important thing to understand with flow rate testing is that it's not the same as printing speed. Flow rate is plastic volume through the extruder per second, which is independent of the line width and layer height. As an example, a 0.4mm nozzle with a 0.2mm layer height printing at 300 mm per second results in a flow rate of 21.4 millimeters cubed per second. Likewise, a 1.2mm nozzle with a 0.5mm layer height printing at just 39.2 millimeters per second also has a flow rate of 21.4 millimeters cubed per second. There you can see a different width, height and speed, but identical flow rates. The test I'm going to run is a single wall test similar to what you can find in the recently popular Orca slicer. My slicer is set up to use 0 top and bottom layers, 0 infill, 1 perimeter, and a brim for bed adhesion. As the Z height increases, the printing speed is increased corresponding to our selected flow rates, from 5 mm3 per second up to 50 mm3 per second at the top. I printed it in ABS with a temperature of 250 degrees Celsius, a 0.45mm line width, and a 0.3mm layer height. This is the final print, and you can see that at the top of the print, at 50mm3 per second, that the hot end just can't keep up. There's loads of big gaps, it's definitely not right. Conversely, at 5mm3 per second, we have a very consistent wall, meaning that the flow rate is well within the capabilities of the hot end. Looking closer at the middle of the print, the limit for this hot end and extruder combination seems to be in around 20 to 25mm3 per second. I'd estimate that it's around 22. Using a flow rate to print speed calculator that I designed myself, and inputting the flow rate at 22, we can see all the limits for typically recommended layer heights and widths for typical nozzle sizes. Notably, a 0.4mm nozzle with a 0.15mm layer height is almost exactly 400mm per second, the quoted maximum speed for the V400. Before we make any conclusions, there are a couple of limitations of this flow rate test to consider. Firstly, it's a combined test, since the hot end is moving around to maintain a specific flow rate. Because of this, it has to slow down for corners, which gives the hot end a bit of a chance to catch up in the event that it was struggling on the high-speed straight sections. This does make it a bit more realistic for some printing scenarios, as you're likely to be creating complex shapes, but it does slightly increase the indicator performance because of the reduced corner speed. The other effect which we have to consider is that during acceleration, the nozzle pressure will be increasing or decreasing, which again has effects on flow rates and can over or under extrude at the start and end of the straight sections, again making results a little bit less clear. So what does this all mean for the V400, and how fast should you be printing? Starting with acceleration, if you want a set and forget value, something in the range of 10 to 15,000 mm3 per second should be about fine for pretty much any nozzle size and printing speed that you decide to use. That being said, print quality at these accelerations may be decreased, so I'd recommend setting any external parameters, the top layer and bottom layer, to whatever is the recommended acceleration value from your input shaping results, as this should net you the best quality. If you're only ever using the included 0.4mm nozzle, you are going to be limited to about 400mm per second. So as a result, you could bump up accelerations to something like 100,000 mm per second squared if you wanted to. But again, ensure that you set quality optimized values for external features. However, if you're interested in some very minor modifications, like switching the nozzle out for a CHT type, you could potentially boost your 0.4mm nozzle printing speeds up to around 600mm per second, with accelerations set to around 40 to 60,000 mm per second squared, giving you pretty insane printing performance. So in conclusion, while my tests indicate that 400mm per second is an appropriate maximum speed, the stock acceleration values of between 4 and 7,000 mm per second square are actually very low compared to what this machine is capable of. Remember though, your printing will only ever be as good as the weakest link. So if you're printing small objects, you may also wish to increase the cooling.